This video gives an introduction to simple continued fractions. We'll discuss some basic concepts. In particular, we'll talk about what we mean by simple continued fraction, and then we'll talk about something called convergence. Let's get started. We'll look at an example to see what we mean by simple continued fraction. This example starts with 4 plus a fraction. The fraction has 1 in the numerator, and in the denominator it has 2 plus another fraction. This next fraction also has 1 in the numerator. In its denominator, there is 1 plus another fraction. This pattern, where we have numbers plus fractions in denominators, continues a couple more times. The next numbers are 3, then 1. At the end, we have 1 over 2. There isn't another fraction in the denominator. It could continue, but it doesn't in this example. There is another way to write this. We can put the sequence of numbers in brackets, like this, with a semicolon between the first and second numbers and commas between the others. This way of representing simple continued fractions is easier to write and a whole lot easier to type. The nested structure you see, where we have a number plus a fraction, and then in the denominator we have a number plus a fraction, and so on, is what makes what you see a continued fraction. But to be a simple continued fraction, there is more we have to say. Notice that all the numbers that appear are integers. In our example, they are all positive, but this first one can be any integer. It can be positive, negative, or 0. The rest of the numbers, though, have to be positive integers, and the numerators all equal positive 1. Let's go over this again, but more generically, using variables. We can write a sub 0 plus a fraction. The fraction has 1 in the numerator, and a sub 1 plus a fraction in the denominator. And the pattern continues just like in the example, except we are using variables. A simple continued fraction can be shorter or longer than the example, so we'll just write dot 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 and indicate that it ends at some a sub n. And if we write it using brackets, it looks like this. Now let's write down the restrictions. The first number, a sub 0, can be any integer. The remaining ones, a sub 1 through a sub n, are all positive integers, and the numerators all equal positive 1. Before we move on to convergence, there are a few more things to mention. Simple continued fractions have values. If the value is a rational number, then the simple continued fraction is finite. It has an end, like the one in our example. That one ends with the 1 over 2 at the bottom. But if the number is irrational, the simple continued fraction is infinite. It goes on forever. You never get to anything like 1 over 2 at the end of our example. And if we're using variables, it doesn't stop at a sub n. We would just have the dot 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 and not indicate that there is any end to it. Our example is a finite simple continued fraction. It represents a rational number. Here is an example of an infinite simple continued fraction. This one starts off the same with 4, 2, 1, 3, 1, and 2. We'll add an 8 and draw a bar over part of it. The meaning of the bar is similar to when we use a bar to indicate a repeating decimal. In this case, the part with the bar repeats forever in the simple continued fraction. Since it repeats forever, this is an infinite simple continued fraction, and it represents an irrational number. Let's shift gears and talk about convergence. Convergents are values of portions of the continued fraction. In each of these portions, we include everything to one of the numbers, in other words, to some value of a sub k, but we exclude everything after a sub k. So a single continued fraction has multiple convergents, one for each value of a sub k. Convergents are typically denoted p sub k over q sub k. The subscript k indicates which value of a is the last one we included. Let's look at an example. We'll use the same continued fraction as before. We can make a little table to keep ourselves organized. The top row is for k, the subscript, which goes from 0 to 5 in our example. We also have rows for a sub k and the convergent p sub k over q sub k. We can fill in the values for a sub k, 4, 2, 1, 3, 1, and 2. Okay, the value of the first convergent is 4 over 1. Let's see how we get this. In the generic case, using variables, We want the value we get if we include a sub 0, but exclude everything after that. In our example, we include the 4, but exclude everything after it. So the value of the first convergent is simply 4. Since the convention is to write it as p over q, we write 4 over 1. Let's look at the next one, when k equals 1. The convergent is 9 over 2. We include a sub 0 and a sub 1, but exclude all of this. So we include the 4 and 1 over 2, but we exclude everything else. Make sure you notice we include the 2 in the denominator, but not the next numerator, just the 2. So the convergent is 4.5. If we write it as p over q, it's 9 over 2. We can move on to k equals 2. The value is 13 over 3. We include a sub 0, a sub 1, and a sub 2, but we exclude the rest. In our example, we include the 4, the 2, and the 1, but we don't include any of this. You can work this out and get 4 1/3, or 13 over 3. We'll just fill in the rest. In a separate video, we'll see an easy way to calculate all of the convergents. For our example, the remaining convergents are 48 over 11, 61 over 14, and the last one is 170 over 39. That last convergent includes the entire simple continued fraction. There isn't anything left to exclude, so it equals the value of the continued fraction. In this case, 170 over 39. So our continued fraction, 4, 2, 1, 3, 1, 2, equals 170 over 39. These are two ways of writing the same thing. Each convergent that we calculate along the way was getting closer to this final value. I'll leave it to you to do some calculations and see if you think they approach the final value quickly or slowly. And the infinite continued fraction we wrote, 4, 2, 1, 3, 1, 2, 8, with this part of it repeating forever, equals the square root of 19, an irrational number. We can't calculate an infinite number of convergents, so we can't keep going and eventually find some p over q that exactly equals the square root of 19. But each convergent gets closer. The convergents are rational approximations of the irrational number. Again, I'll leave it to you to do some calculations and discover for yourself if the convergents that we already have provide a good approximation for the square root of 19. For example, would you say 170 over 39 is close to the square root of 19? Do you notice anything else about the convergence? To recap, we talked about what we mean by simple continued fraction and looked at something called convergence. That's all for now.